Hi guys, welcome to this. I hope to be a quick recording. So it's for this two questions that some of you have had, and it's mainly has to do with the normalization of a wave function. So, in a nutshell, what the normalization does, it takes the probability density, which is defined as the basically the amplitude square of the wave function, and summing it from the entire space where the electron is supposed to be, and then stating that it has to be one. In other words, there is a 100% probability that the electron is somewhere where it's supposed to exist. That's basically in a nutshell what it is. And that makes it easy because when you're trying to find the probability, for example, for a specific measurable quantity, like for example, the position of the electron in a specific interval, then you just integrate in that interval and that's it. You don't have to divide by the sum of all the possibilities, which is one, which is 100% really. So that's why you do the normalization. So again, we have this problem in here, and it gives you a wave function. So let me look at this wave function quickly in here to see it. Again, I'm looking at the solution here that you guys have seen. So they gave us a wave function already where the total energy is zero, and they asked us to find the potential that makes it this possible for the electron to be from zero to infinity. You can think of this one as some sort of a long carbon chain where we are sitting on one side of that carbon chain looking at the entire molecule. So in this case, the electron is contained between 0 and infinity on that side. So you can think of it that way, where its wave function is imposed to be this one. Okay, so we found the potential. Once we found the potential, basically solve this equation. Once we find the potential, we find indeed that it has a minimum, as it's supposed to have some sort of a stable position around which it can vibrate or oscillate or do some stuff in there. Anyway, so we found that. Now the task is to determine A, which is supposed to be real, in terms of B. Okay, so that's the whole really purpose of this exercise in here. So what we're saying in here is, let me get the one note. So what we're saying in here is that this wave function, which is supposed to be A times exponential of, I'm sorry, before the exponential, there is a square term in x. So there is an x squared, and you have an e to the negative x squared over b squared. Let me quickly look at it to make sure I didn't miss any terms in there. Okay. Yeah, it's ax squared exponential of negative x squared over b squared. So if you're wondering about that b, it's just a scaling factor to make the dimensions work. In other words, the dimensions of x and b are the same, which is usually a length, which is a meter. Okay, so that's one thing. So obviously in here I have a meter squared, and I have a meter squared over meter squared, which cancel to give me the exponential properly well behaved. So really have to have the proper dimensions for a. Okay, to make this one probability density, that means this one over the entire volume between 0 and infinity, that is the space with which the electron is confined, must be 1. So obviously psi squared in here better have the units of 1 over meter to cancel this meter, okay, because there is a dx that has a meter. So a has to have the proper units because it's square root. The square root of a times a meter coming from times a meter squared in here. So that is psi. When you square this number, oh, I don't have to, sorry, the dimensions of a times the meter squared. I'm trying to get too many things. The dimension of a times meter squared, the whole thing squared, times, it must be of the same units of 1 over meter. Obviously, you move the meter in here correctly, and you do the dimensions of a squared times meter to the power 4 must be equal to 1 over meter, and a itself must be of the order of 1 over a square root of meter to the power 5. Okay, from the get-go, we see that since b is carrying the dimensions of the entire problem, I should see a b to the power 5 in here in the denominator in the expression form. So without doing anything, I know that a is proportional to 1 over the square root of b to the power 5, just to make the dimensions work. Okay, that was lesson number 1 in physics, dimensions. Okay, so, and you can get a lot out of it. So we know that a, the amplitude of this wave function, must have a b to the power 5 in the denominator. If you did this, you could get a lot of credit because the other number is just a number. It's like 1. Okay, so let's find it. So what we're saying in here is 1 must be equal to a squared. We're assuming it's real, so we don't have to worry about its phase, times the x to the power 4 exponential of negative x squared divided by b squared squared, so it means I have to put a 2 in here, times dx, the integration from 0 to infinity. I'm going to make this one as a variable y, okay, so that the integral is of the exponential is easier to handle. Or should I make it a y squared? We have to make it a y squared because they give us this hint somewhere, okay? Because we don't want to really carry this integration at the end. So they give us this hint. So we're going to take advantage of that. So we need the y squared in the exponent. So, which means that square root of 2 over b times x is actually y. That means that the dx transforms as b over square root of 2 times dy. So we have this part now. We have this part. All we need is the x to the power 4. We can get it from here. X to the power 4 is the same as y to the power 4 times b to the power 4 divided by 2 to the square root of 2 to the power 4 over 2. I'm going to leave it as such, okay, for right now. I know 4 over 2 is 2. So, what we're saying in here is that 1 is equal to a to the power 4 times, we're going to put these constants in here, b to the power 4 over 2 to the power 4 over 2 times the stuff in here that is coming from the dx, which is b over 2 to the power 1/2, okay? And then I'm left with the integral from 0. The boundaries of integration do not change because x and y are proportional to one another. X equal to 0, y equal to 0. X goes to infinity, y go to infinity. So boundaries of integration do not change. Now I'm left with y to the power 4 coming from this x to the power 4 and exponential of negative y to the power 4. Squared because of that. And we have a dy. You see, we have the b to the power 5 already. And that's exactly what I thought we should have. Okay, was there a square root of pi or somewhere? No, not yet. Okay, well, this integral is given. So we really don't have to do it. You can go Feynman on it and find it, but it's given. Why do we have to bother? It's 3 square root of pi over 2. So let's plug it in. So this is 3 square root of pi over 2 over 8. Was it 8 or 2? Over 8. Okay? 8. So I'm going to write it 2 to the power 3. So I'm going to write this 8 as 2 cubed. Because I like this 2 appearing everywhere in the denominator. As a matter of fact, we are going to leave just the square root of 2. So this one is going to render back to 2 over to the power 2. So I have 2 and 2. 2 and 3, that's 5. Okay, so the expression look like this then. 1 equals 2. Why is it a to the power 4? It's a squared. Oh man, sorry. Okay, so this is not power 4. So it's just a square the a and becomes a squared. So this becomes a squared times b to the power 5 because of these two b's. And then you have 2 to the power 3 and 2 to the power 2. That's 2 to the power 5. And finally you have 3 square root of pi over 2. And that's basically in a nutshell what the answer is. So at the end of the day, we found that a is equal to the square root of, I have 2 to the power 5, which is 32. I think I may have put initially something like a 128 or something. I thought it's to the power 7. No, it's to the power 5. Divided by 3. And then b to the power 5, as it should have, times square root of pi over 2. Under the square root. Okay. Oh, I'm sorry, 2 over. I have to invert this one in here. So there is a 2 over pi. Okay. So let me make sure. 32, 2, 3, 2, yeah, square root of 2 over pi. Because you're going to invert that to find the a. So the a has that 2 over pi. So here is the answer. Well, square root of 2 over pi, it's like 2 over 3. So this is about 1. Okay, I know you're going to say it's not exactly 1, 0 0.7 or 0 0.9, I don't care, it's 1. Okay, it's about 1. 32 over 3 is about 10. Okay, square root of 10 is about 3. So this whole thing is something of the order of 10 to the power 0, basically, like 3 or 4 or 5 or 2 or something. Okay, and the main thing is this b to the power 5 over 2, as it should, because the dimensions have to have a b to the power 5 in here to make all of this dimensionless, because it's supposed to be 1. Okay, so we could have answered most of the problem by just basically doing a dimensional analysis. You go to the lab and you indeed find this dependency over b to the power 5 over 2, where b is the significant dimensions in the molecule. So that's basically where the electron is supposed to be. If you're going to do measurements, for example, it doesn't matter whatever you're doing. Resonance, it doesn't matter what you're doing. Electrical properties, dipole properties for that molecule. B is going to be the significant measurement in here, in this case, if that wave function is indeed the solution to the problem. So I'm not sure exactly if there is a realistic case for it, but that's the point I'm trying to say in here. Then the scaling factor for that wave function, when you're doing calculations for anything that is measurable, if you want to normalize it and divide by that number, it will have to have 1 over square root of b to the power 5 in it, times the number that is going to be about 1. Okay, 3, 2. I mean, if you're curious, trying to find the exact number, well, just take the square root of 32 divided by 3 times the square root of 2 over pi. That is the actual number scaling the b to the power 5 over 2 in front of it. Okay? Okay, so that's really hopefully answers that question. The key thing in here is that you normalize the function, the wave function. Is it really something that you can measure in the lab? Absolutely not. It's just a calculation trick so that you don't have to do this integral over and over and over trying to measure any other quantity. If you have to do it 1,000 times, you're going to divide by that factor. And if you're going to plug it in the computer, you may end up with a lot of time wasted. But then if the wave function is normalized, you're just integrating the number, the top part, which is just a probability between 0 and 1. So that is basically the key in here for that. Okay, I know some people sometimes they make a big fuss over this normalization stuff, but it's just math at this point. It's not physics really. Okay, the physics part of it is just to make this problem easier to handle mathematically. Okay, which brings me to the second question from another problem, and that is, let me pull it first, from this one, and it's trying to find the probability of finding the electron in the 1s state also between 0 and a naught. Okay, it also asks to check this wave function. So this is already given to you as a solution to the Schrodinger's equation for the case of a hydrogen atom. So we know this is a specific real problem. So this is not like the first one, which is a hypothetical problem. So this is a real physical problem. So the wave function depends only on r. That means theta and phi do not exist, which means that the problem is symmetrical with respect to these numbers. Okay. Again, we're imposing, or at least we're trying to calculate now. So let me go back into my OneNote. So let me write the wave function in here into my OneNote. So psi 1s, it's the 1s state, is equal to 1 over square root of pi a naught cubed exponential of negative r over a naught, where a naught is significant dimension number in this case, which turned out to be exactly a Niels Bohr's radius for the hydrogen atom. Okay, anyway, so we're checking in here. We're not saying it is, but we are checking. So this is not a statement, but rather a question. So the integral from 0 to infinity, the integration over dr, because the element of volume in this case is 4 pi r squared dr. The part with theta and phi has already done, and it's 4 pi. So the only thing that is left for us is to do the integration over the spatial term, which is the radial term, dr, from 0 to infinity, of the wave function squared, which is 1 over pi a naught cubed exponential of twice this number when you exponentiate, when you square the exponential, you double it. Okay, the pi and the pi cancel. Okay, and this thing has to be 1, so A naught should disappear from these calculations. Let's check. We do change a variable. This time we're going to call this whole thing just y. Okay, so which means that my r first is equal to A naught over 2, I'm sorry, over 2 times y. Because if I sub A naught cancels the A naught, the 2 cancels the 2, and I'm left with y. Okay, so that gives me dr then equals to A naught over 2 dy. Okay, all of the dimensions now are carried out by A naught because y is dimensionless. As you can clearly see, y is the ratio of r over A naught. And if r is in meters, A naught is in meters, they cancel, and at the end of the day, y is actually has no units. And that's good because you want the exponential to have no, the exponent to have no units. That's actually a requirement, okay? So now, what it says in here is that does 1 equal to the integral from 0 to infinity of 4 times r squared? And we know what r squared is. It's A naught squared over 4, because the square of 2 is 4, times y squared, and dr, which is an A naught over 2 times dy, divided by this A naught, divided by this A naught cubed, times the exponential of negative y. Okay, the A naught and the A naught, and oops, not the last, not the y naught squared, and the A naught cancelled. Okay, that's good. And furthermore, the 4 and the 4 also cancelled. So what we're left with is does 1 equal to 1 over 2 the integral from 0 to infinity of y squared exponential of negative y dy? That's a question, it's not a statement. Let's check it. Well, we do this by parts. This is my function, this is my default function, which is negative of exponential of negative y. Okay? So by parts, we're going to have a 1/2 in here, and we have a y squared in here, the integral from 0 to infinity, minus and minus, so there is a minus in here and minus in the formula, so this becomes 1/2 the integral from 0 to infinity, the derivative of this function, which is 2y, times the exponential of negative y dy. So then the other negative is gone with the other negative, so I don't have to write it again. Now this part of the integral is 0. Why? Because in the upper limit, I have exponential of negative infinity, which dominates the power in here, so I'm going to get a 0. In the lower limit in here, I have a 1 in here, but I have a 0 in here, so it's going to be 0. So it's 0 minus 0, which is 0. So the question then boils down to the following. Obviously, the 2 and the 2 cancel. The question then is, does 1, so it's still a question really, not a statement, does 1 equal to the integral from 0 to infinity of y exponential of negative y dy? Again, we're going to do it by parts. This part is my function, and this part is my d sub negative of exponential of negative y. Now, the part in here gives me negative y, exponential of negative y, between 0 and infinity. Minus and minus is a plus again. The integral, the derivative of y is just 1. I'm left with an exponential of negative y dy from 0 to infinity. Obviously, you're wondering about the negative sign. What happened to it? It's in here. It has been consumed in the other negative that came from the formula. Well, this part in here is 0 also, because in the upper limit, the exponential dominates the power law. So I have 0. And the lower limit, I have 0 minus that. So it's going to be 0. 0 times 1, which is 0. So at the end, I have 0 over 0. So the question then becomes, does 1 equal to the integral from 0 to infinity of exponential of negative y dy? This is simply exponential of negative y evaluated between 0 and infinity. Well, at the infinity, I have 0 because exponential of negative infinity is 0. Minus and minus, so it's going to be a plus exponential of 0, which is 1. So this is 1. So indeed, 1 is equal to 1, therefore the wave function is normalized. That's part 1. Part 2. To this problem in here, it asks for finding the probability of finding the electron between R1 equals to 0 and R2 equals to A naught. So the first part in here is to deal with the boundaries of integration. So R1 goes from 0 to A naught. Y, so I'm going to do the same technique, except the boundaries of integration now change. So my Y now If R1 goes from 0, y is 0. If R1 is equal to A naught, y has to be 2 because 2 over 2. In other words, y is equal to 2 R naught over A naught. So when R naught, there is no such a thing. Okay? R over A naught. So when R is 0, y is 0. So when R is equal to A naught, y goes to 2. So the integration now becomes from 0 to 2. So those complete integrals, you have to be careful with them. They are not necessarily 0 because the upper bound changed on you. So the probability of finding the electron between these two positions is going to be equal to, because this wave function is normal, technically I'm supposed to divide by all the possibilities, but they just normalize this wave function, it's 1. So I'm dividing by 1. So that's the whole technique for normalization. So it's the integral from 0 to A naught of the dV times psi 1 s squared. Okay? Again, the volume in here, it's still given by 4 pi r squared dr. So with my suitable change of variable, everything should be fine. Okay? So this probability then is equal to the integral from 0 to A naught. Let's still deal with r. It's 4 pi r squared dr times 1 over pi A naught squared, A naught cubed, I'm sorry, exponential of negative 2r over A naught. Obviously, this becomes my y. This will have a, so it's going to be the same thing up to which point? Up to here with 1/2 also in front of it. Okay? So it's going to be this probability, and the boundaries of integration is the only difference in here from 0 to 2 instead of from 0 to infinity. So this probability then, P12, must be equal to 1/2 the integral from 0 to 2 of, I think, y squared exponential negative y dy. Okay? Double check on it. I think it's in here somewhere. Yeah, y squared exponential negative y dy. And the boundaries of integration are from 0 to 2. So it's going to be the same thing, except the boundaries of integration change. So this is my dy and all of that stuff, that good stuff that we did earlier. So it's y squared with a negative exponential of negative y between 0 and 2. Minus, minus, so it's going to be plus, and the 2 cancels the 1/2. So I'm going to be left with the y exponential of negative y dy between 0 and 2. Again, the upper limit is not 0. So this is going to be equal to 1/2 times negative 2 squared, which is 4, exponential of negative 2, minus 0 times 1, which is 0, because 0 squared is 0. Okay, now the other integral in here is going to give me also y, exponential of negative y, between 0 and 2, plus the last integral, again, the negative minus the negative, is going to be 2, exponential of negative y dy. Okay, so that's really what the whole thing boils down to. Well, this is 0, of course, but this one is not 0. Negative 4 over 2, that's negative 2. So I have negative 2 exponential of negative 2. And in here, the upper bound again is negative 2 exponential of negative 2, because I have 2 in here and the good stuff. And the last term in here, plus exponential negative e minus y between 0 and not infinity 2. Okay. Obviously, this is negative 4 e to the negative 2 plus the upper bound is exponential of negative 2 minus minus, so with a negative sign in here, remember I have a negative sign in here, and there is a negative in here. So the point is 1 minus 5e to the negative 2. That is really the whole thing. I already had it on GeoGebra, or I did not, I guess. So I have 1 minus 5e to the negative 2. Negative 2, not positive 2. Okay. And let's pick up just, no, 3 decimal points. Let's do 3 sig figs. This is the same thing. Okay, it's 0.323. So that's the value of this probability. Again, it has to be less than 1, more than 0, because it has to have a finite probability. After all, this is the situation. So this probability is 32.3%. So here is the situation. The integral of this wave function between 0 and infinity, this wave function had no, so it is an exponential. It's like this. It's decaying like this. So this whole thing is 1. This entire surface is 1 because it's 100%. We just found it to be 1. Namely, the integral from 0 to a naught, so this is r, by the way, and this is the wave function now. Obviously, this is incorrect. This surface is not that of psi. This is of psi squared. So remember, what I'm plotting in here is psi 1s squared, okay? The probability density, and this is its area, which is 1. Now, if I integrate the same quantity between 0 and a naught, it's this integral. Obviously, this integral is less than 1. Because if this whole thing is 1, so this is, it turns out to be 32 or 0.323, okay? So that's why the whole trick for here, so that's the probability of how much what chance we are going to get in order to, I mean, how much probability do we have for an electron to exist between 0 and a naught for the case of the hydrogen atom in the 1s state, okay? I hope that this is helpful. If you still have any questions, please reach out. Thank you. Where is my mouse?